In the previous lecture, I gave you some promises about what deep learning can do, and now in this one, I'm going to try to make you, to convince you that I wasn't trying to deceive you. So basically, we're going to start by reviewing backpropagation and the way of training the networks with stochastic gradient descent. Some of you already saw this in the machine learning course, but this is an important part of this course. So we're going to look at this in some detail and review this matter. And then we're going to look at different architectures and examples, and also on this important aspect of how deep learning handles features and data in general in order to solve the problems that we want solved. And then I'll try to explain a bit why the success was so recent. We saw that machine learning and artificial intelligence are with us already for several decades, but deep learning really took off in recent years. So we're going to look at why the recent success with this approach. And then I'm going to give you some specific examples of architectures and applications, not in order to see them in much detail, but just as a sort of motivation to illustrate how versatile this approach can be and how it can be adapted to many different types of problems. So let's start with backpropagation. This is the basic algorithm for training neural networks, and this is what we're going to use in general to train our models. There is some additional things that we have to do, for example, in reinforcement learning, but most of the work, computational work that's going to be done for training these models will be with backpropagation. So the idea that we have here is the basic piece for building these models is the neuron. And here we have this linear combination of the inputs that are multiplied by weights, which are the parameters we're trying to adjust. So all these weights are the adjustable parameters for our optimization. And then this weighted sum is computed and passed into an activation function. We saw with the Rosenblatt perceptron that the activation function was just simply a threshold function that outputs 0 or 1, but we can have different ways of modeling this. For example, instead of having a threshold here, we can add an additional weight here. Let's pretend that we have an input that is always stuck at 1, and then we have an additional weight here that feeds into the weighted sum, and this is some sort of nonlinear function. So this additional weight will work the same as the threshold, and we can have some activation function here. So this is quite flexible. We can change the activation function, but the idea is always the same: a weighted sum of the inputs into the activation function, and then out comes the output of the neuron. Now, if we want to minimize the error, we're going to have to slide down our error function, and we need to see in which direction we have to go. So this is the basic idea of backpropagation, is that we're going to use the derivatives of the error with respect to all these parameters in order to help us find a way to some local minimum that we want to find for the error function. If we use the original threshold function from Rosenblatt, we have a problem that we cannot compute the derivative here. So it's either 0 everywhere, or here we cannot determine the derivative. So this does not give us the necessary information to slide down the error surface and find the best point. So one possibility, this is a classical activation function for neurons. We're going to see later on that this is actually not a good activation function in most cases, but it's the best, the most well-known example, so we're going to use that to illustrate. If we have this sigmoid activation function here, then we can compute the derivatives, and we can find a way to go down the error surface and minimize our loss function. So let's consider an example where we are training a single neuron, which is something like this. The activation function is this sigmoid function, and the loss function, the error function that we want to minimize, is this quadratic loss function. So basically, S would be the output of the neuron, for example, J, and this Tj would be the desired output, the target value for the output, for example, J. And now we want the sum of the quadratic errors over all the examples that we have in our training set to be as small as possible. This 1/2 factor here is really not relevant for the minimization, because if we minimize this expression, we have the same parameters regardless of whether we have that constant there or not, but it simplifies the derivative because of the square there. When we compute the derivative of this expression, these two cancel out and we get a simpler expression here. So basically, we usually write the quadratic loss function as 1/2 the sum of the quadratic errors, because it simplifies the derivative afterwards. But now the idea is that we need to find the derivative of the error with respect to the weights that we are updating. Note that the error is measured here. It's the difference between this output and the target value. But what we are changing are these weights all the way here in the back. So we need to compute the derivative of the error with respect to each of these weights in order to know in which direction we need to change the weights. So we can do this by the chain rule. We can multiply the derivative of the error with respect to the output of the neuron. So it's this expression here. For the quadratic error, this is the derivative. Then we multiply that by the derivative of the output of the neuron with respect to the input into the activation function. So this is the activation function, the sigmoid function. The input into the activation function is this net sum of, or this weighted sum of all the inputs. So we need to compute this derivative. This is the derivative of the sigmoid function here, and so we have this derivative, and then we need to go one more step and compute the derivative of this weighted sum with respect to each weight. But this one is easy because since this is just the product of the input by the weight that is contributing to the sum, the derivative with respect to the weight is just the value of the corresponding input. So this is the expression that we have, and so the update rule for the single neuron will be to give a small step in the direction where the derivative is going down. So we take a small step in the direction of minus the derivative of the error with respect to this weight that we are updating, and this expression is given by the multiplication of all these derivatives. This minus sign will cancel out with this one, and so basically we have this for chaining all the derivatives, and we take a small step in that direction. It's important to take a small step because as we change the weights, then all these functions will change too, because now we have different parameters in the neuron, and if we take a step that is too large, we may not converge into the right place. So usually we take small steps. In this example, for a single neuron, you can use, say, 0.5 or something like that. When we have a large network, then usually the training rate may have to be quite low in order to prevent things from oscillating too much. But the basic idea is that we have a target here. We are measuring the error between the output of the neuron and the target, and now we compute the derivative of this error, the activation function, and the weighted sum. So chain all these derivatives in order to find out how to change one particular weight in order to improve the similarity between the target value and the output of the neuron, so reducing our loss function. Okay, so this is the step, but now how we're going to use these steps to train the whole network. And the implementation of this for training the network is usually done in this way: stochastic gradient descent, which is called the gradient descent because at each step we are trying to slide down the gradient of the loss function, so looking at the derivative to find out in which direction we have to take a step. And it's stochastic because we are presenting examples in random order. One way of doing this, we could present one example, compute the direction of the step, take the step there, then present another example, compute the direction of the derivative for going down this surface for another example, and so forth. Note that even though the surface, this surface would be for the average error over all the training set, but each example in the training set is only contributing a bit to this surface. So it may give us slightly different directions as we are computing the derivatives using each individual example. So this will give us the stochastic nature of the gradient descent. We are on average going down the average error surface over all our training set, but each individual step is going into a random direction depending on which example we are picking to take that step. A more efficient way of doing this is usually to use a batch or a mini batch if you want to use part of your training set, in which first we use a set of examples to compute the derivative. So we are not changing the network, not changing the weights, but using a set of examples to compute the different derivatives for each example, and then adding those vectors all together to update in one go for all these examples. This tends to be more efficient because we don't need to change the network all the time. We can do this in parallel, different examples, doing all the computations in parallel and so on. And also it can give us better information about what the right direction should be. On the other hand, if we use batches that are too large, we lose this stochastic nature of gradient descent. This should be a C, not a G, because now we are not randomizing so much the directions we are going into, and so and this randomness can help us escape some local traps in the loss function. So usually there is a trade-off between the size, using too many data points in each batch, which can make it more difficult to escape those traps because we lose this randomness, or using batches that are too small, which makes learning very slow because now for each very few examples we need to update the whole network, and we have less information about the gradient in very small batches. So if we do this with a single neuron, we already saw we have this linear classifier. We can reduce the error. So in this case, we are using the sigmoid function to try to approximate the classification here. 1 for the red points, 0 for the blue points, for example. And we are propagating the error all the way to the weights in order to change the weights that are multiplied by each coordinate in the data. So this is just for a single neuron, and a single neuron is not very useful because it's only a linear classifier, and we have better ways of solving these kinds of problems of linear classification without using the neuron and training like this. But the power of the neural network comes when we start stacking neurons into deeper networks. For example, a multilayer perceptron is a dense network in which each layer is fully connected to the next layer and so on until we reach the output layer. So there is this is a feed-forward network because the input is passing on from one layer to the next. There are no loops here, and it's fully connected because each neuron on one layer is fully connected to the other layer. So in this case, we have just a very simple multilayer perceptron, which has the inputs here. Then we have one hidden layer of 2 neurons, and these are all connected to the output neuron, which is the second layer. So we only have 3 neurons in 2 layers. So let's see how we can train this network. And this is really this was the innovation of backpropagation, because with the Rosenblatt perceptron, we already knew how to train one single neuron. The problem is what happens when we stack neurons in layers. Now, to train the output neuron in backpropagation, we just use the same algorithm as for a single neuron with backpropagation. The only difference is that the output neuron is receiving as inputs the outputs of the previous layer. So basically, if we have the same example where we are minimizing the quadratic error using a sigmoid activation, this is the same expression that we used before. But now when we are computing the how to update the weight of this output neuron here, so any weight of the output neuron here, what we use to multiply this part, this expression here, is the output of the neuron from the previous layer. So this SIM would be the corresponding output of the neuron from the previous layer. We are not reaching yet the input values here because we are trying to update this weight. We have the error there at the end, we propagate all the way here, and we need to consider the output that is passing through the weight. But you can see that there is this part that is a function of the neuron, the activation of the neuron and the error propagated so far. And then we are going to use, let's call this a delta for this neuron. We are going to use this one, this same value for all the weights in the neuron by simply multiplying by the different values that pass through those weights. So for example here, we use this delta multiplied by the output of this neuron, Y1 to go through this weight, to update this weight, but then we use the same delta multiplied by the output of this neuron to update this weight here. So basically we can compute these delta values for each neuron and then simply update the weights by doing this multiplication between the delta and the value that is passing through the weight, so to speak. So for the output neuron, this is simple, but for the hidden layers, the neurons that are inside the network, we need to keep propagating backwards. So the way we do this is we have this this sum for the error propagated through all the neurons that are in front of our neuron. For example, in this case, when we are computing for this particular neuron, we have to consider the error propagated through this neuron on the output layer. And if we had several neurons in front, we would have to add the contribution of all of them. So this is the sum that we have here. But we are always doing the same thing, chaining together the derivatives by multiplying them. And then we keep the propagation through the activation function and through the weighted sum of this particular neuron that we are considering. So basically we are taking the deltas of all the neurons in front multiplied by the weights they are passing through. For example, in this case it would be the delta computed for this neuron multiplied by this weight. This would give us the contribution of the derivative of the error for this particular neuron, and then we keep backpropagating that through the activation function and the corresponding weights until we update this particular weight for the neuron. And then we keep going backwards through the network to propagate the error through all the layers. So intuitively, what we're doing here for a hidden layer neuron over here is computing the derivative of the error with respect to the output of this neuron, and then the derivative of the activation function, and then passing through this particular weight, and this would be one term in this sum here. And then we do the same for the other neuron in front, the derivative of the error function, the activation function, and the weighted sum here, and also contribute the other term in this sum for updating the weights in this neuron. So as many neurons we have in front, that would be the number of terms in this sum here. And then we propagate through the gradient of the activation function of this hidden layer neuron and all the inputs that are passing here for the different weights that we are going to update. So this is the intuition, but as you can see, with backpropagation, we are simply chaining together the derivatives of all these functions. Irrespective of what the network architecture is, as long as we add up all the relevant contributions for each particular neuron, we can compute how to update the weights of that neuron. So basically, what we're going to do when applying this algorithm is first propagate the input through all the layers to compute the activations. So when we present a vector to our network, we're going to compute all the activations going forward in our layer. Or if you want to think of this more generally, we are going to look at the way the neurons are connected, and we're going to feed all the inputs into the first neurons, and then the outputs of those neurons into the next neurons, and so on. So we're going to propagate forward the activation of the network. And then once that is done, we're going to compute the errors for the output neurons, and we're going to compute the derivative. So in this case, if we are assuming a quadratic error and a sigmoid activation, it would give us this expression, but we would simply have different expressions for other loss functions and activation functions with the same general idea. We are computing the activation values and the derivatives, and then we're going to chain together these derivatives by multiplying all the values of the derivatives at those specific points. So this would be done in backpropagation. We are going to keep multiplying all those derivatives until we reach each of the weights we want to update, and the result of multiplying all those derivatives will give us the direction in which we need to update the weights and by how much we need to update the weights. So now we update all the weights, and we keep doing this. We can do this for each example individually, or as we saw before, we can do this for a batch of examples, compute all the updates, add up all the updates, and then update in one go for a multiple set of examples, which is more efficient because that way, since we are not changing the network between different examples, we can compute this in parallel. So if you have a GPU or something like that with lots of processors, you can easily compute a lot of examples in one go and make training much faster. So as you can see, as long as we have functions for which we know the derivative, we can generalize this for any kind of architecture that we want and adjust the parameters. We just need to propagate the input through all the layers. No matter how complex the architecture, we use the output of each neuron as the input of those that are connected to that one. Then for the output neurons, we compute the error, the loss function, and as long as all the activations and loss functions have derivatives that we can compute, we can backpropagate these derivatives back through the whole network in order to find out how to adjust the parameters. And then we update the weights, and we can generalize this for different activation functions, different architectures, loss functions, and so forth. So as you can see, with this basic algorithm and the basic element of the neuron, we can now create different architectures for different problems, but always use the same general approach for training these models. So let's see what we can do if we stack, if we go beyond the single neuron and we use an additional layer here before, a hidden layer. What we are doing is that these two neurons in the hidden layer are transforming the data we input into the network and changing it so that the output neuron is actually looking at the different shape of points after this transformation. So this is the original data here, and this is how the data seems like when seen from this output neuron, because this output neuron is not seeing the original values, but is seeing the activations of the hidden layer here. So as you can see, the hidden layer is transforming the data and make it easier to separate it with a single line. It's making the data linearly separable. This output neuron is still just a linear classifier, but since it's now operating in the transformed representation of the data, it can classify it linearly, and when we project this classification back to the original space, it's this bent line here. So after going through the transformation of the two hidden neurons. And this is possible because these neurons are independent of each other, and each one has a nonlinear transformation, that sigmoid function, for example. So when we combine these two nonlinear transformations, we get something that is different from the original data, and it can help us solve the problem. And one very interesting property here is that the nonlinear transformation itself is learned in the model. Note that we can do this kind of things with support vector machines, for example, but the nonlinear transformation will be fixed by the user. We decide how to do the transformation, what kernel to use, and so on, and then the model tries to do the best it can with that specific transformation. In this case, the transformation is being learned as we train the network, and it's part of the model itself. So this is where deep models derive their power to solve generic problems. For example, if we have a more complex data set here, we have this data set with the red points in the center and blue ones around. And now we put two hidden layers. And this is what happens after the transformation of the first hidden layer, the second hidden layer, and now the output layer will just separate red and blue. So in this case, the representation here is simply the index of the points and the output of this layer here. But you can see that because of the transformations, now with a linear classifier, we can separate most of the points easily because of what's happening in these hidden layers. So basically, we can increase the power of our models and create very powerful models by stacking neurons. For example, this would be in a multi-layer perceptron, but this is just one possible architecture. We're going to see a lot more different variations of this, but the core idea is always the same. We connect the neurons, we use backpropagation to train them, and the model will learn how to transform the data in order to optimize solving the problem that we want. So basically optimize the target functions that we are using in backpropagation. So let's see an example between this approach and the classic machine learning approach with shallower models. We saw linear models, for example, logistic regression. We can separate only when the classes are linearly separable, and humans must choose the right features. So we can, in theory, solve different problems with this, but we need to choose the right features so that the resulting data set has the classes linearly separable, and the linear classifier can solve our problem. So this requires lots of manual intervention because we need the right features for this to work. With a nonlinear transformation, for example, support vector machine, we can, in theory, go beyond this linear classification, and in theory, we could solve any problem if we found the right features and the right transformation. But once again, we need to not only choose the right features to use for training our model, but we also need to choose the right nonlinear transformation to solve that model, always balancing the problem of overfitting and adjusting correctly to the data and so on. So if you want to solve a classification problem with, for example, support vector machine, you need to choose the features that you're going to use and choose them carefully, and you need to choose the kind of kernel that you're going to use, what will be the nonlinear transformation in order for the model to work properly. Because at the end, after this nonlinear transformation, things must be in a way that they can be linearly separated by the last step of classification. Now, with deep classifiers, we have a very different approach. With a single neuron, it's not an advantage because that is just logistic regression. But as we stack neurons with nonlinear activation functions, we can create a model that learns different representations of the data at different parts of the model, and then of the network, and then uses those different representations to solve the problem at the end. So we can think of this as a series of nonlinear transformations followed by a simple linear classifier, which will be the last neuron on the network that is giving us the output. We saw an example of this here. We have two steps of nonlinear transformations that keep changing the data, and then the final neuron is just a linear classifier that is working on the final representation the model learned for the data. So this will be the general approach of a deep neural network. And we can see here that there are two important differences between this one and the classical machine learning approach. First is that these nonlinear transformations, we do not have to choose them. It's the actual network that is learning how to transform the data. And because of that, because we don't have to fix what kind of nonlinear transformations we're going to use, we don't have to provide the appropriate features either. We can just dump all the data into the network and let the network figure out what things are useful or not. So this makes deep learning very different from general machine learning, because it requires a lot less investment in feature selection and in choosing the model and so on, because now the fine-tuning that we can do will be adjusting the architecture of the network, regularization and things like that, but the actual transformations that are being done and the way the model will use the features will be determined by the model itself. So these layers, this is an example with a convolutional network because it's easier to visualize. I'm not going to explain now what a convolutional network is, but we're going to look at that in more detail further on in the semester. But these represent what kinds of patterns in the input images. So these are used for image classification. These figures represent what kind of patterns in the input image stimulate each neuron or provide result in a greater response for each particular neuron. And we can see that at the first layer, the neurons are responding to very simple patterns like these contrasts in diagonals, in horizontal and vertical lines, and so on. But as we go on into higher layers, we start seeing neurons respond to more complex patterns like circles and curves and things like that. And then as we move on, we see even more complex patterns like these stars and so forth. So the network is learning different representations, different ways of identifying patterns in the image, so that when we reach the last layer that will choose how to classify each image, it already has the appropriate features for doing that classification. So we are effectively automating feature extraction inside the model that we are using, for example, for classification. So this results in a different approach to data. We saw in machine learning in the last semester that in general it's useful for machine learning to use structured data. We have a table where, for example, each row is an example, each column is a feature, and these features are well defined. They have some semantics, some meaning in some context. For example, it's about the clients of some company, and we have the amount of money they spend per year on average, their age, gender, things like that. And these, we know what the features are and what the table means. And all the examples will have the same set of attributes. So all our clients have values on that table, and they all have these attributes specified. And each value, each column in the table means the same thing. So we have a column for age, a column for expenses and things like that, and the value there always has the same meaning. And this is the easiest data to deal with when we are applying the classical machine learning algorithms. However, it is also data that takes a lot of effort to maintain, because someone has to fill in those records each time a client comes into the store or something like that, and there's a lot of human work in curating that data and maintaining structured data. So this is basically the advantage, is that it's easy to use, but the disadvantage is that the data does not structure itself spontaneously. Humans must constantly intervene to keep data structured. Then we have data sets that have a mixture of structured and unstructured data or semi-structured data. For example, the logs of a server, it's not really a table. You cannot put everything in a table, but you have some structure there because they're usually generated by automated systems that conform to some specific syntax and semantic for the different symbols. So this is not trivial to use in machine learning raw, but we can, with some effort, extract features from there because it's all so we know what the records are. We have a very well-defined syntax, and so we can extract features from those. But note that this will also require human intervention if we want to convert these semi-structured data into some table of features in order to feed into a support vector machine, a random forest, or something like that. But most of the data is probably in unstructured format. This is video, text, audio records, images, things like that, where we don't have a formal specification of what is the meaning of each element, and we cannot easily transform, for example, images into a table because we cannot really tell if they have dogs there or cats or things like that, and the kind of features we can extract manually will probably be very generic, like computing the entropy of the image or how much red, green, and blue it has, some things like that. So this is very difficult to use with classical machine learning, unstructured data, because it requires a lot of work on the part of humans to extract the appropriate features before trying to train a model. So this work also requires a lot of expertise, a lot of specific algorithms. For example, for text mining, we have things like trying to find the roots of each word so that we can put together words that are just variants of the same. We can try to extract these concepts and things like that, and keywords and so forth. But this requires specific algorithms to process the test that must be developed by humans in order to convert free text into tables of features. The same thing for image processing and classification. So classical methods would use algorithms for detecting the threshold for the image, and then edges and histograms and things like that, that were designed to try to maximize then the performance at doing some classification task. But this takes a lot of work, and if the problem changes a bit, then most of this work will have to be redone and fine-tuned and so on. So it's very hard to use classical machine learning approaches to deal with this rich set of unstructured data that we have everywhere. But the idea of artificial intelligence would be to have the machine solving the problems and not us. So this kind of approach where the human laboriously extracts features, selects a nonlinear transformation and so on in order to use some model is not really very good, not only more in a more philosophical aspect of what artificial intelligence should be, which should be the computer solving the problems, but it's also not very good when we are dealing with problems that change rapidly. For example, anything today involving technology, internet, and things like that, it keeps changing all the time. And also anything that has an adversary. For example, if you have a very good model for detecting credit fraud that uses some specific features and then transforms them in some particular way, then the people who commit fraud will probably discover that if they do something slightly different, your model will not be able to catch what they're doing, and now you're going to have to do it yourself redo those steps of feature extraction and so on in order to adapt. So when we need either to use lots of data, complex data sets, or change things very rapidly, it's very hard to keep doing this by hand. Deep learning can solve these problems because by stacking all those nonlinear transformations that are learned by the model during training, we can automate these feature extraction steps and the selection of the appropriate transformations. The network is doing all of those things as it learns to solve the problem. So this makes it much more powerful. It allows us to solve problems even when we don't know what the right features should be. We don't understand very well the problem, but the network can solve it. And it allows to respond quickly to changes in the problem simply by retraining the network or fine-tuning the network for different conditions. So this is just a classical example using Mitchell's autoencoder, just to show that how deep learning can learn useful representations. And we can do this even without labels, so with unsupervised learning. This, what I'm representing here are 8 different possible inputs, which consist of a 1 followed by 7 zeros, or 0, 1, and then 0, and so on. So basically, we have a vector of 8 values, but all of them must be 0 except one of them, which is 1. And we are listing here the 8 different possible values in our data set. And this would be a network that has 3 hidden layers, 3 neurons in the hidden layer, sorry. So the hidden layer has these 3 neurons, and then the output layer has 8 neurons. And what we're trying to do is to train the network to output the same as we give it as an input. So this does not seem very useful. This is what's called an autoencoder. It's a network that just echoes back whatever we give it. But the useful part comes here in the middle, because the network has to convert these 8 input values into something from which it can reconstruct the original 8 input values. And this something can only have 3 values. So it needs to compress the data and find a compressed representation. When we start training the network, since the weights are all at random, we get rubbish. So when we put in this vector of 1, 0, 0, 0, we get something that has nothing to do with the input, and so on for all the different examples. So these are different outputs and the corresponding inputs that the network is giving us at the beginning before training. But once we start presenting these examples using stochastic gradient descent with backpropagation and fine-tuning the weights of the network, after training we get this result. So when we input this into the network, we get the same thing outside. It's approximately the same thing. We can see slight variations in the shades of gray because the network may not give us exactly 0 or exactly 1, but it's close to 1 or close to 0. So we minimized the reconstruction error here. And we can see that for all the examples, we have an output that is very similar to the input. So after training, the network can give us back what we gave it. But the interesting part occurs here in the activations on the hidden layer. You see that the network had to learn to encode the 8 different inputs in different representations of 3 values in order to be able to decode it back into the 8 different outputs. And we can see that the representations here are the 8 combinations of 3 0 1 values. So we have 1 0 1, 0 0 1, 0 1 0, and so on. And we have basically taught the network to encode these 8 different inputs into combinations of bits, of 3 bits, basically. So this is just a very simple example, but it shows how we can, even without labeled data, we can train the network to find good representations of the data. So this is using the UCI banknote dataset. This was the first assignment for machine learning last semester. We can use PCA, for example, to represent this data in 2 dimensions because the original data has 4 dimensions. each banknote is represented as 4 numbers, 4 features manually extracted from the images, and we have the class of the fake banknotes and the real banknotes. And if we use principal component analysis, we can project everything into 2 directions that preserve most of the variance. So we're going from 4 dimensions into 2 dimensions, preserving most of the variance, and we get this representation here. So we can see there is some difference between fake and true banknotes, but there is a lot of overlap in this projection. We are not capturing very well the structure of the data in this way. One thing we can do is to use an autoencoder, and this is the architecture of the autoencoder I used. So we have 4 values as input, then we have 6 neurons, 4, 2, and then we go back symmetrically, 4, 6, and the output of 4 values again. So basically we are training this network to create a representation in this hidden layer of 2 neurons, from which it can revert all this encoding and find the original values again. Now we're going to train this with the data without looking at the labels. We don't care about the labels. We are just training the network to reconstruct the values, the input values, but in the meantime, recode everything into just 2 dimensions. And when we use this encoding, so just this part of the network, to project our data into these 2 dimensions, we get a much better separation between the 2 classes. So our autoencoder learned a manifold for representing the data that captures much better the structure of the data. So this is, autoencoders give us a very good example of how deep networks can learn useful representations of data, regardless of the problem that we're trying to solve. So in this case, we are just requiring that the output be the same as the input and just looking at the structure of the data. This is an example of using unsupervised learning with deep learning. This ability to automatically encode the data can then be used in many ways. For example, typically we can have lots of data that is unlabeled and only a small subset that is labeled. So with this approach, we can try to learn how to extract useful features with unlabeled data that usually is a lot more than what we have labels for, and then apply those features for classifying the labeled data. So the question now is, why did deep learning have this success now in recent years and not before? Because as we can see, this idea of neurons and neural networks dates back to the mid 20th century. Even if we consider that backpropagation only appeared in the 70s, we could in theory have deep learning in the 70s, but we only had this success in recent years. So one problem is that when we have very powerful models, and deep neural networks end up being very powerful because they have lots of parameters that we can adjust, and all those stacking of nonlinear transformations can transform the data in many different ways. We have a problem of overfitting if we don't have enough data. So as we can see, this is a sort of just a visual representation. If we have smaller data sets on this side, then we can do fairly well with classical machine learning, but not with deep learning, because then we have a big overfitting problem. We don't have enough data to specify, to find the correct parameters for our models. But as the size of the data set starts to increase, we start reaching the limits of what we can do with that basic approach where we manually select the features and manually select the nonlinear transformations for support vector machines or things like that. And deep models increase their performance. So at some point, if we have enough data, deep models can start to outperform the classical approaches. So this is one of the requirements for deep learning to really be useful, is that we have lots of data. So we can see here an example. In 2006, there was this competition for image classification, And there were this Caltech 101 dataset. They had these 101 categories, and they had about 50 images per category, so for each class of images. This varied from 400 to 800, but on average it was about 50 for each category. And classical computer vision models could get this top 5 error of about 26%. So if we looked at the best guesses for the models, they would get it wrong about 26% of the time. So with this kind of data set, deep learning was not very useful because you had very few examples for each class. Also, computers were a bit slower, so it was hard to train these models then. But then we had some improvements in algorithms. For example, the rectified linear unit. We're going to see this next week, and pre-training and things like that improved the way these deep models were trained, and also better hardware. So one big boost for this was general purpose GPUs, where GPUs could be used for general computation and not just for images, for synthesizing images. So, and this way it was very easy to train neural networks using this massively parallelized processing, and so it speeded up a lot the training. But nowadays we have very specific circuits for this. So the tensor processing units from Google and the Nirvana from Intel, we have these processors that are specifically designed for training deep neural networks. And these large data sets and better computation really changed the whole game. Because now, for example, in 2012, the ImageNet dataset came out, so this competition for classifying images, but this one had 1,000 categories and more than 1 million images, so around 1,000 images per category. And with this large data set and general purpose GPU, large convolution neural networks became dominant in this competition. So from this point onwards, those classical computer vision approaches where humans specify the kind of features we extract and so on, no longer could compete with deep models. In 2012, the top 5 errors, so this is the error for, this means that 15% of the cases, there was no accurate guess in the top 5 categories the network proposed. We give an example to the network, it will give us the most likely 5 categories it considers the image to be in, and it was making a mistake 15% of the time. When we consider that there are 1,000 categories, this is pretty good, because 85% of the time it would give us the correct category in that top 5, and only 15% of the time it will make a mistake. And this was much better than computer vision methods. But over the years, as we increase, as we go through better and better networks, you can see that the error keeps decreasing. So nowadays we have networks that are basically at the same classification error as humans themselves. So with this data set and some labels that are a bit questionable and humans may be a bit undecided in the category they put the images, we are reaching the level of human performance in this problem. So this is an example, the first one, this AlexNet. It was trained using 2 parallel, so the model was split into 2 parallel streams because of the limitations of this NVIDIA graphics card. They only had 3 gigabytes of memory each, and so since the whole model for training required more than this, they had to split the network into 2 separate streams that was then combined at the end. But even with these limitations, they managed to have this 15% top 5 error. The second best classifier was a classical computer vision approach that had 26% error. So it was far below the performance of this convolutional network. And this is basically the set of convolutional layers that we have. I'm going to talk a bit more about convolutional layers, but we can think of these as having a single neuron that is scanning the input overall, the image, and producing a map with the outputs for each of these steps. So we have these different convolutional layers doing these computations, but we have millions of parameters here to adjust for all of these layers. And at the end, we have dense layers. So we have layers of neurons that are fully connected, and then 1000 output neurons that will give us the guesses that the network is making for the different classes. So then this is a more elaborate and more a larger network in 2015. This got a much lower top 5 error, the Google Net, and you see here all the convolution layers and the complex architecture with different outputs at different levels and so on. So this I'm not going to detail this network here, but it's to give you an idea that we are not prisoner to that specific multi-layer perceptron architecture. We can really put these things together in different ways. These different colors represent different modules, which are themselves a few layers of convolutions and pooling and things like that, that then are stacked along in this complex architecture. And then we have different ones. These ones you can easily use yourself. You can download and use the networks. For example, VGG19 is available in Keras, and this one can 75% of the time gives you the actual the real class of the image on top for this ImageNet database, and 92% of the time in the top 5. The ResNet goes to 97%. So we have these networks that have a really high performance in classifying images. However, they are a bit heavy. They are large networks. They took a long time to train, but now you can download the trained network and use it. And then we have specific examples. For example, this eNet is used for real-time semantic segmentation. Instead of just classifying the image, it can tell you which pixels belong to persons, to animals, to planes, and things like that. And it can do so in real time. You can process video, for example, and it keeps track of what's happening in all those images. Then you have these smaller networks like ShuffleNet that you can use on a mobile device to identify objects in images and things like that. So there's a lot of versatility in how we can build these architectures and how we can adapt the networks to different problems. And there's also this interesting property in that while it takes a lot of computation power to train the network, it takes a lot less computational power. Sometimes it's still considered, but a lot less than for training when we want to use the trained network. So if someone already trained the network, you can download the network with all the weights and just use it yourself. So this is an example from this paper of 2016 that generates visual explanations for classifying images of birds. And I'm just going to give this example to show you that this is not just about classifying things or just about dealing with images and things like that. You can do lots of interesting things with these deep models by combining different architectures and different problems, solving different problems together. So what these authors did for this paper was to use this Caltech birds dataset. We have 12,000 images in 200 categories of birds, and for each image they obtained 5 sentences describing the bird. So this was actually obtained from humans using the Amazon Turk feature that you can hire people to help label images or other data sets, and they obtained descriptions of what the birds look like for each image. And now what they are training is trying to find a match, not only for classifying the image of the bird, but also giving a short set of sentences that explains why that bird was classified in that way. So the interesting part here is that they combined a convolutional network for image classification with 2 recurrent networks that generate the sentences. So we're going to talk about these kind of networks later on, but these long short-term memory networks are networks that work like this. We have the same module that you can imagine as if the same module was repeated in several layers, or that you have the output of the module being fed back into the same module. So this is why it's called a recurrent network, but it's the same model. There are some different activation functions here and weights that we are computing. I'm not going to detail this now, but what happens is that this block of neurons is receiving as input the output of the previous iteration of the same block. And now you can train this for sequences, for example, of words, and it will capture a representation of the sequence of words. But you can also feed inputs into this module and then check the output of the module and feed it back in and use it to generate sentences. So after training, it can generate sequences of words by looking at this sequential outputs of these models. So what these authors did was they have this convolutional network that classifies the birds, but also produces a representation of the images, and this is concatenated with the classification of the bird, the class of the bird, and is used in the recurrent network to generate sequences of words describing the bird. And here they had some a combination of loss functions that would tell the relevance of the words giving the class label and the previous words, because we need the sentences to make sense together. So we were judging if the sequence of words was actually one with a high probability of occurring in natural language in all the data set of sentences that we have, but also that the words that occurred were tendential discriminative. They were more probable for that particular class of bird than for other classes of bird. So basically, you see we have two different loss functions here that we are optimizing, but we can just aggregate them together, use backpropagation, and train the whole thing. And now with this, we have this kind of output from the network where you have the image of a bird. The network classifies the bird and then generates a description like this is a pine grosbeak because it has a red head and breast with a gray wing and a white wing and so on. So the sentences are not very good grammatically and so on, but they capture what are the important aspects here. So yellow bird with a black cheek patch and a black crown and so forth. And so we can use the network not only to do the classification, but also to generate this kind of outputs, these text sentences. So there are lots of other applications recognizing unstructured data like speech, images, video, and so on, doing translation, and even doing generation of images and video. So if you look, you can find on the internet an NVIDIA demonstration where they trained a deep convolutional network to generate video of driving through town based on actual video. So this has a sort of dreamlike feeling, in that in the short term you can see the sequences of images, they make sense as if you are driving in the city, but you don't have an actual city, so it makes no sense. The map where you're going to, the direction and so on is not there. There is no model of the city, there are just images being generated. And you can also generate images of faces. There are examples there of generating people that do not exist, or for fashion, etc. And now the question here is where we are in this hype cycle. So we saw that in the early stages of artificial intelligence, there was a lot of hype, a lot of promise about what artificial intelligence would do in the late 1950s. But then we had this lots of inflated expectations, but then a great disappointment when those expectations were not met. The same thing happened with neural networks. and several times in the perceptron of Rosenblatt, for example, in the 90s and so on, when artificial neural networks started to take off again. But then people found out that they were mostly overfitting because they did not have enough data to actually work with those kinds of models. And now the question is whether we already reached this level plateau where things are working and now they are working as expected, or if we are still at another peak and we're going to have a big disappointment. So I'm hoping, for the sake of the usefulness of this course, that we are already somewhere around here, and you'll find the techniques you learn here useful in the future. If we go down in a disappointment valley, well, my advice would be wait a few more years, because eventually they will get this to work. So what you can do now during the week, I suggest you play a bit with the TensorFlow Playground. If you go to this site, you can build your own networks, choose some data sets and train them and see how the different representations are changing. But this is just to illustrate the kind of things that I've been showing here. It's nothing serious, so if you want, just take a few minutes to play around with this. And you can try different numbers of layers, different activation functions, and so on, and experiment with this. What I would like you to do for next week, before we have the tutorials, is to set up the software that we're going to use. So if you are using Anaconda, like in last semester, you can install TensorFlow 2 just by using conda install TensorFlow. This will install the basic CPU version. If you have a GPU card from NVIDIA, so with these chipsets from NVIDIA, and if you have the right CUDA version, so you can install easily with this conda install GPU. If you don't have the right drivers and so on, maybe it will not work with the GPU, but either way, if you install the GPU version and you cannot work with the GPU because of the drivers, you will just get a message and it still works with CPU. So you can choose which one. In any case, we are going to try to give you examples that are simple enough to run without a graphics card and just on an average laptop. So we're not going to use very complex examples, and I think that even the basic installation with CPU will work fine. Alternatively, if you don't have time to install Anaconda, or if you want to try out, you can use Google Collaboratory. You can go to this site for Google Colab. You need to log in with your Gmail account, but then you have access to a Jupyter notebook where you can import TensorFlow and execute code and so on. The thing that you need to do is, since we're going to use data files, you're going to need to link your Google Colab to the Google Drive so you can use the files. And this is just a set of instructions that you need. You import this drive module and mount your Google Drive. This will give you a link to a special code that then you have to use Google Drive to authorize access. But once you do that, you'll have from your Jupyter notebook, you'll have access to the Google Drive that you mapped. So you can put your files there. You can save your results to a file and so on. So you can use this easily without much setup, but I would advise you to use a local version. It's probably more practical for your assignments and the exercises, because Google Colab requires you to keep the connection live. You cannot just leave things running. You have some limited memory and limited time for computation and so on. So but I think it's best to use a local installation, and if you already have Anaconda, it should be easy to set up TensorFlow for use. So to sum up for now, today we saw this idea of the nonlinear transformations, the stacking these transformations, and how artificial neural networks and backpropagation works to allow us to train these deep models. And the big advantage of deep learning is essentially that part of the model is automating feature extraction, so we can use a much wider range of data that we could easily use with the classical machine learning, where humans must extract the features. And if we have enough data, then these models can solve much more complex problems, because the models themselves learn how to find the correct features. The main reasons why only now has deep learning started to have some significant success is basically the algorithms for training the networks. We're going to see some details about activation functions and optimizers that are important, the hardware that we have to deal with these large models, and in particular the amount of data. You need a lot of data for this to work properly, and if we don't have large amounts of data, then deep learning will not be very useful, and that happened for quite a few years. So if you want to read more about this, you have some in the lecture notes. I put the reference for these papers that I talked about, and you also have these chapters of the book. Okay, so I'll finish for now. I'm going just to log in to Zoom, and we can talk a bit in the Zoom session if you want. So see you soon.